Hello, and welcome back to the Diffusion and Osmosis pre-lab notes. You should have already watched part one. This is part two, a closer look at water potential. So it says right there, the first bullet, that water potential measures the tendency of water to diffuse from one compartment to another. So we just said that water will go from an area of higher water potential to lower. We're going to look at some different situations and what affects that. So here you have the equation for water potential. Quite simply, if you want to determine the water potential of a solution, use this symbol. But you also need to know what is the pressure potential and what is the solute potential of that solution. Add those two things together, and that's how you're going to get the overall water potential. So based on this equation, the measure of free energy of water, aka water potential, has two components: pressure potential and solute potential. You'll have to forgive my awful handwriting. It's very hard to write on the screen. Okay, so thus the predicted movement of water is influenced not only by solute, but also pressure. Because previously we were talking about hypertonic and hypotonic solutions, and that you could use the amount of solute to predict the movement of water. But it turns out that pressure is a really big component to that too. I mean, just think about like a wet sponge, okay, full of water, but then you can squeeze that sponge and expel the water out of it even faster. So pressure is going to play an important role in which way water is going to move as well. Let's look at a cell as an example. So let's say that this diagram is looking at a plant cell. So this outer, thicker layer is going to be the cell wall. The inner layer, this dotted line, would be the plasma membrane or the cell membrane. Okay. And we also previously mentioned that within the cell, that there are going to be other structures that have membranes to them. And in this case, you can talk about a central vacuole. Right? So what's inside here is going to be water, H2O inside of that central vacuole. Okay. Now it says if the cell is placed in pure water, and we're looking at the cell's appearance over time, we notice that, well, water must be moving into the central vacuole, thus expanding. More time goes by, more water has gone in, but also water can start to come back out, because now we've increased the pressure of the vacuole and the cell membrane and the cell wall, and then it prevents additional movement of water inside the cell. So I'm going to say, actually, in this moment, in this picture, there wouldn't be any more water moving in. There actually may be water coming out because of that excess pressure. So we can describe this last cell as being, spelling it wrong, turgid. Okay, it's got a lot of pressure inside, which is causing the water to go in the opposite direction. So what I wanted to say about this picture is that by moving, water can perform work. In this case, expanding the cell, for instance, making it turgid, making it plump up. So this potential in water potential is referring to that capacity, the capacity of the cell, of the water to do work. So if a solution has high water potential, that means that there's a high potential for that water to perform work. All right, let's look at this scenario. It says the figure below represents 4 different setups. Predict, by drawing an arrow, the net movement of water. So water could still go in both directions, but net movement is what is the majority, which direction is the majority of the water moving. It says, note that the initial concentration of solutions on the left and the right side never differ. So what we're saying is we always have a 1 mole solution okay, and pure water on each side. So pure water here, still a 0.1 mole solution here. Pure water, zero point 0.1. Pure water, zero point 0.1. So same for each, okay? And the other thing I want to add is imagine that the membrane separating the two sides of the U tube, the original U tube, are impervious to solute. So that means that the only thing that's going to happen, the only thing that can move is going to be water. So I'd like you to take a look at this scenario. Okay, notice your water potential values are listed at the bottom of each of the situations. Pause the video and make a prediction by drawing an arrow inside of one of these boxes. Which direction would you expect the net movement of water? And then when you're done, resume the video. Okay, so let's go over the answer and see how you did. In scenario A, on the left side, the water potential is 0, and on the right side, the water potential is negative 0.23. That means that the left side has a higher water potential than the right side, and water will go from high to low. So your arrow should be moving in that direction. Okay. In scenario B, again, 0 water potential on the left, 0 water potential on the right. So this one was a little tricky because water would be able to move equally in both directions. Okay. Third scenario, letter C, the higher water potential is now on the right side and the lower water potential is on the left. 0.07 compared to 0. Okay, and then in this one, negative 0.3, negative 0.23, negative 0.23 is a higher value than negative 0.3. So let's explain though, because right below it wants us to explain what's going on here. Okay, so in figure A, the water has a net movement from the left side of the U tube to the right side. Okay, and the question is why? So for this one, it's kind of simple. The pure water, again, forgive my handwriting, the pure water has a higher water potential. Okay. In figure B, the water, we're going to say, has no net movement. Why? Well, the water potentials are equal, but the difference between what happened in the second scenario is this pressure component, right? So the pressure potential was matched exactly to the solute potential of that negative 0.23 that we saw previously. So when you have positive pressure, you kind of negate the solute that's there, setting water potential equal to 0. So you actually can have a solute present. This would be hypertonic compared to this side and still have no net movement of water. So tonicity is not the full story. You have to really take into account all of the components for water potential. So for the Y here, I'm just going to say added pressure to the right side set those water potentials to be equal. In figure C, the water has a net movement from the right to the left. Why? Again, positive pressure. But this time we upped the pressure, 0.3. Solute potential was negative 0.23, so that actually gave us a water potential of positive 0.07, which was more than pure water, right? So again, the right side has a greater water potential. Right side has a greater water potential. due to increased pressure. Okay. And then last one, figure D. This one's a little bit different. Tension is also considered negative pressure. So you can see on this side, they're actually pulling up. So they're relieving pressure on this side. And let's see, when you have negative pressure and pure water, that gives you a water potential value of negative 0.3. On the right side, there was no pressure applied. Okay, so pressure is 0. The solute is still there, so it's negative 0.23, giving you that solute potential of negative 0.23. But because of this negative pressure on the left side, decreasing water potential more, that's why water moved from the left to the right. Or backwards, I said, from the right to the left. Okay. So for this one, the Y, there was negative pressure on the left side, decreasing water potential on the left. Okay. All right. I'm going to stop there with this video.